Hey, AP Chemsters, this is Mrs. Blankwalle bringing you Chapter 6. This is our first discussion about energy, and this is a really important subject in AP Chemistry. I will guarantee you there will be an energy question on the AP free response. It's one of those promised kind of a questions. That in equilibrium you are guaranteed to have on the AP. So pay special note to this, very important. So let's just look at the title here, thermodynamics. And when you hear the word thermo, what do you think of? You're thinking of what? Heat, all right? Dynamics means motion. So heat is moving. It's always moving from one area to another. And so we're going to investigate where is it coming from and where is it going to in this chapter. So in section 6.1, you can read about chemical hand warmers. We're actually going to do a lab with chemical hand warmers, and we're going to determine what substance we can use to make the best hand warmer. And there they introduce you the definition of thermochemistry. It is the study of relationships between chemistry and energy. And it's a very, very important relationship. Again, I can't stress you enough that this chapter is a really important one. We're going to learn about this relationship, okay? So what is energy? So we're going to learn some more definitions here. So the energy, which is symbolized as a capital letter E, the clinical definition, the one that physicists will use, it's the ability to do work and or produce heat. Well, what is heat? This is important because we're going to talk about heat a lot. So what is heat? Underline this, star this, highlight this, whatever you need to do. Highlight is the flow of energy caused by a temperature difference. Okay, it is a flow of energy. What does that mean? Energy is moving. How does it move? It can move through heat. Okay, so it's a flow of energy caused by what? A temperature difference. Okay. Excuse me. Energy is also the sum, S-U-M. What does that mean? You're going to add. It is the adding of or the addition of potential and kinetic energy in a system. And this is also known as the internal energy of a system. Will you please underline that, the internal energy? We're going to be talking about that later on. So what is the internal energy of a system? It's the sum. You're going to add the potential and the kinetic energy of that system. All right, well, what's potential energy then? Potential energy is the energy by virtue of position. You might recall back from earlier days that if I have a book on a table and a book on the floor, which one has higher potential energy? It's the one that's on the table. Because if I knock it off, all right, it's going to move. It's going to go into the downward force. You can't really knock the book down from the floor if it's already on the floor, so it doesn't have a lot of potential to do work, okay? So the one higher up on the table has more potential to do work, okay? So how is that related then to chemistry? Normally we don't talk about, you know, tables and books and things like that. What's the potential energy in chemistry then? It's the chemistry that is usually the energy stored in the bonds, okay? So when the atoms are sharing those electrons one way or another, okay, there are forces of attraction between the nuclei and the electrons. So that is what you're tapping into when they say you burn your gasoline. That's where the energy of your car comes from, is taking the difference between the attractive forces of your reactants and your products, okay? It says when the bonded atoms are separated, the potential energy is raised. Why? Because it takes energy to separate the bonds. Why? Because it's called the Coulombic attraction. And we're going to talk more about that later. There's a formula for that between the nucleus and the shared electrons. And that's what you are, like I said, tapping into when you're talking about chemical reactions. That you always start a chemical reaction with breaking bonds. And that requires energy always. Okay? Why? Because you are separating those attractive forces, and that requires energy. So what do you think is going to happen? So that's half of a chemical reaction when you break bonds. What's the other half of a chemical reaction is when you form new bonds? Well, guess what? I know it's not written down here, but think about it. If it requires energy to break bonds, what's going to happen when we form the bonds? What are we going to do? We're going to release energy. It's the opposite flow, if you will, of energy. So you're going to require energy to break bonds. You're going to release energy to make new bonds, okay? And that's the energy of a chemical reaction. Now, what about this kinetic energy? Where does that come from? Well, atoms and molecules are always moving, so there is kinetic energy. We talked about that with gases, but that is true with liquids and solids. What do you mean? Solids are moving, and actually they are. Okay, so there's vibrational energies, rotation, like flipping around, doing like somersaults, if you will, like the energy or the Earth rotates. And this translational energy occurs in molecules, and it's like like a water molecule with oxygen in the center and the hydrogens are off it. They're like on springs, if you will, and they can have what we call translational energy. We already discussed this with the gas laws. Kinetic energy is proportional to the Kelvin temperature. Kinetic energy depends on the mass and the velocity of the object. Kinetic energy equals 1/2 mv squared. You should have heard that before a few times anyway. We also have something called the law of conservation of energy. Do you remember Lavoisier had the law of conservation of matter that says that mass can either be created or destroyed in a chemical reaction? Nuclear, yes, but in a chemical, no. Well, that same thing is true for energy. That means energy cannot be created nor destroyed in a chemical reaction. So what does that really mean? That it's just changing positions, if you will. It's flowing from one area to another. So, but the net total energy is still the same. So there is a graphic down below that actually shows this. So let me get that one ready. So there is something that's really, really important called system and surroundings. This is something else you may want to highlight and star and underline here. We're going to be referring to this a lot in this unit, okay? So what is the system? The system is what's being investigated. The surroundings is what? Everything else. And the key idea for your surroundings is what exchanges energy with the system. So here's my graphic. So here's my system energy gauge. For right now, we don't have any numbers to it, don't have any units with it, but it's kind of like your gas tank, all right, empty to full. So before the energy transfer, it's like at half point. So your system, what you are investigating, has a certain amount of energy. And then the surroundings, well, what's the surroundings? It's everything else. Has another energy system or energy gauge, and it's halfway to empty from from the full or from the midpoint, so it's about a fourth, if you will. So if I added up all these units, I have 2 units here and 1 unit here, so my total energy adds up to 3. So now what happens? All right, can you see what's happening here? The system goes from halfway to, it loses some, doesn't it? It loses a whole unit over here, doesn't it? You start out with 2 units, and after this energy transfer, you lost energy. Now there's only 1 unit left. But wait a minute, over here in the surroundings, you started with 1 unit, but obviously it gained some energy. Where did it gain it from? It gained it from its system. The system gave the surroundings 1 unit of energy. What does that mean? Maybe it got hot and maybe you're warming your hands over a fire or something. So the system would be the fire and you are warming your hands. You're the surroundings. You're gaining the energy from the fire. That's my example. But what do you notice about your total energy? We have 1 unit here and we have 2 units here. We still have a total energy of 3 units. So what might we say here? That the system lost energy, but the surroundings did what? It gained energy. And what does this say? It says the surroundings gained the what? Exact amount of energy lost by the system. Okay, so I think you can tell there's some key ideas here that you always have a flow of energy. Now, does it have to be the system giving energy to the surroundings, or can the surroundings give energy to the system? Yes, it can. Okay, so we can do the reverse as well. But what's the key idea? If we even reverse it, you're still going to have the same amount of energy that you start with as you end with. Okay, one thing gains, one thing loses. You're going to lose the exact same amount as you gain. And oh boy, is that going to be important later on. Okay, so if you need to make a note to yourself, please do so. Hey, let's see what the next page brings. Okay, let's talk about some units of energy. You've already heard about this from our last unit, the gas law unit, about kinetic energy being measured in joules, Joules, all right? You had an activity to start this whole unit where we investigated the relationship between joules and calories, okay? So here are the exact numbers. 1 kilojoule is 1,000 joules. 1 little calorie is 4.184 little joules. Remember, I made a distinction between little calories and capital calories. Capital calories are your food calories. So if you look at your food label, it's in a capital calorie, and it's 1,000 little calories. So a kilojoule is 1,000 joules too. So the idea of kilo is important here as well. And then you have something called a kilowatt hour. We really aren't going to use that a whole lot, but there it is. It's 3.6 million joules. Okay, so convert the following. All right, so how many calories are in 85.6 kilocalories? Why don't you go ahead and pause this and work that one out. When you are done, come back and join me. All right, how'd you do? Well, I set it up this way. I put 85.6 kilocalories, put 1 kilocalorie on the bottom, 1,000 calories there on top. So I got 85,600 little calories, okay? So this would be your food calorie, and this is what we do in chemistry class. Letter B, how many joules are there in 134.5 little calories? Why don't you set that one up? And if you have to, go back and look up here at that relationship. I believe your equation sheet is going to give you that 4.184, but if not, you're going to use it so many times in this unit, you probably have it memorized anyway. But why don't you pause this and do letter B? All right, welcome back. Let's see how you did. Hopefully you got it. Factor labeling here, so my calories cancel out, joules are on top, and there you go. So why don't we stop here and join me back for the section 6.3. And I'll end with the don't wait to be great. See you next time. Bye-bye.